In this section, we'll cover logistic regression for predicting more than two classes. There are several extensions to the standard logistic regression when the response variable y has more than two categories. The two most common approaches are ordinal logistic regression, which is used when the categories have a specific hierarchy, like class year, freshman, sophomore, junior, senior, or a 7-point rating scale from strongly disagree to be 0 to strongly agree to be 7. The other approach is nominal logistic regression, which is used when the categories have no inherent order, like the color of the eyes, blue, green, brown, hazel, etc. For example, we could attempt to predict a student's concentration or major, y is equal to 1, being computer science, y is equal to 2 if statistics, and 3 if physics. The goal is to predict the class concentration given some predictors. For example, number of p-sets per week and how much time a student spends in the library. There are two common approaches for the nominal logistic regression: one versus rest, OVR, and true multinomial logistic regression. The one versus rest, OVR, approach considers one logistic regression model per class versus the rest. For example, if there are 3 classes, then 3 separate logistic regressions, each to be fitted separately. The probability of each category now is predicted over the rest of the categories combined. So for the concentration example, 3 models will be fitted. First model will be fitted to predict CS from stat and physics. Second model will be fitted to predict stat from computer science and physics combined. And the third one will be fitted to predict physics from CS and stat combined. A picture is worth 1,000 words here. In this example, we see 3 classes: red, blue, and green. Classifying these 3 classes can be turned into 3 binary logistic regressions. The log odds of being blue versus other, red and green, is, as in the binary classification, linear with x. So the probability of B divided by the probability of other, the log of that will be some parameter beta B times x. The log odds of being green versus the other is also linear with x. And the log odds of red similarly will be linear with x. So we fit 3 binary logistic regressions, and from that we can predict the probability of blue, red, and green. The probability of blue will be the logistic function 1 over 1 plus exponential minus beta b times x, and similarly for the green and the red. Close examination of these probabilities reveal that they do not always add to 1. We can solve this problem by simply normalize them by dividing by the sum of all 3 probabilities. So the new probability, the normalized probability for blue, will be the probability of blue given by OVR divided by the sum of the probability of green, blue, and red together. We can normalize, of course, the probability for green and red. So the sum of the normalized probabilities now is equal to 1, and each one of the normalized probabilities will be between 0 and 1. Worth noting that sklearn normalized the output of each of 3 models when predicting probabilities, so no need to do extra work and normalize here. Another option for multi-class logistic regression is the true multinomial logistic regression model. In this case, one of the classes is chosen as the baseline group. Think of y is equal to 0 in the typical binary logistic regression. And the other classes, k-1 classes, are compared to it. Thus, a sequence of k-1 binary models are built to predict being in class Q as opposed to the baseline class K. The log odds, again, being in class Q versus the baseline group is again linear with x. This is mathematically equivalent for using the softmax function to express the probabilities for each class. Now the probability of y is equal to q in the softmax function will be the exponential of beta q times x divided by the sum of e to the beta jx. The softmax function guarantees that the sum of the probabilities is equal to 1 and that each group is bounded from 0 to 1. To determine the coefficients beta q in the multinomial logistic regression, we minimize the categorical cross-entropy loss function, which is very similar to the binary cross-entropy, except here we use the indicator function, which takes values of 1 if y is equal to q, otherwise it takes the value of 0. Simply speaking, we just sum the negative of the log probabilities of the prediction for the correct class. How does true multinomial compares to OVR? Multinomial is slightly more efficient in estimation since there are technically fewer parameters and is more suitable for inference and group comparison. On the other hand, OVR is often preferred for determining classification. For each observation, we simply just predict the probabilities for all classes using separate models and choose the highest probability. In practice, they give very similar results in estimating probabilities and classification. We now turn into classification for more than 2 categories. When there are more than 2 categories, there is no guarantee that the probability will be higher than 0.5 for any one category. So any classifier based on logistic regression will still have to select the group with the largest estimate probability. As a result, the classification boundaries here are much more difficult to determine. And for that reason, we'll provide code to help visualize the boundaries in the exercise given.